Bell's theorem for noisy fields is very different than we expect if we think about an experiment as about particles flying around within it. A noisy field is much more sensitive to the experimental apparatus that contains it than if we think of it as about particles and particle properties. Noisy fields are not differentiable, so we can't use differential equations. We have to use statistics in some kind of way. An event in a device is caused by its noisy surroundings, not by a particle hitting it. And so, of course, if we change the surroundings, then the statistics of events will change, and we can measure those statistics. Now, it's often said that quantum mechanics is incomplete, so people try to complete it by adding hidden variables and in other ways. But what I'm going to suggest here is that classical mechanics is incomplete precisely because we have no-go theorems like Bell's theorem. However, I'm also going to point out that we can easily, and we indeed should, extend classical mechanics to be more like quantum mechanics. So I'm not calling quantum mechanics into question at all here. It's just that an experiment is what it is. If we have an extended classical mechanics that can describe any experiment that can be described using quantum mechanics, then we can't say that the experiment is quantum or is classical. It just is what it is. Our description is not the same as the experiment itself. So here's a particular experiment. This is from Gregor Weihs in the middle 1990s. And what I particularly like about this is that his schematic is so clear about what he's doing. Particularly, he talks about there being a pump in the center of the apparatus that is pumping a noisy electromagnetic field, as I will say. He doesn't talk about shoveling particles into the apparatus. And then he changes that, he modulates it with this other apparatus so that events happen at the silicon avalanche photodiodes that Alice and Bob both have in a way that violates the Bell inequalities. So as well as these APDs, avalanche photodiodes, Alice and Bob both have a polarizer that splits the light into two pieces that can be detected separately by the two different APDs. And then you have a modulator that changes the polarization from by nothing at all or by 45 degrees, depending on what the random bit generator value is, either 0 or 1. And then Gregor also wonderfully clear about what he is going to record. He records the time at which the signal out of an avalanche photodiode changes, together with which of the avalanche photodiodes there was the event happened on, and what the setting for the modulator was at the time. So he doesn't record the signal out of the APD every picosecond. He only records the event time, together with the APD setting, the APD number, and what the electro-optic modulator setting was. And so this compressed record can't be analyzed for other signal details that we might perhaps be interested in. Now it is interesting to look at what the range of frequencies are for the avalanche photodiode. To begin with, there's the optical frequencies at petahertz scale, which is 1,000,000 times faster than the electronic scale of nanosecond for how long it takes for an event to happen. Then we also have the thermodynamic rate, about 1,000 times slower than that, but more than 1,000 times slower, of how often the events happen, once every 10 milliseconds or thereabouts. And then we have the human scale of 1 Hertz, and of course we have the project scale, where it takes several years for an experiment like this to be done. So that is the order of 100 million seconds, considerably slower than microhertz. So when Gregor performed this experiment, he got experimental results. And here is a graphic of 15,000 of those event pairs. Because Alice sees almost 400,000 APD events in a 10-second period, which is how long this is from here to here. But Alice and Bob see only 15,000 event pairs that are coincident within 3 nanoseconds from top to bottom here. So every one of these events corresponds to a coincident sudden rise on 2 signal lines, and so there is a signal line somewhere that changed from near zero to a higher level and has been recorded as an event, and so as an event pair. And of course, when they both record an event As you see here, the majority of these in the color scheme I've used are green or yellow because he set up the pump and the central apparatus just right. Then we have for the diagonal where the electro-optic modulator bits and the avalanche photodiode bits are the same. We have the red and the blue for the lower diagonal and yellow and green for the other two diagonals, which is where we see most events. So if we take that graphic and turn it on its side and add up the number of events of different kind in 100 different vertical slices, we obtain these 16 histograms. And we can add up the numbers of events in those 16 histograms and get these 16 numbers here. We can pump those into this calculation, which is a standard calculation of a violation of the Bell inequalities, 2.714, bigger than 2, a violation of the Bell inequalities. So what we've done here is we've taken a completely classical set of data on a computer hard drive, and we have applied a completely classical algorithm, and we produced a number for which classical mechanics says this is not okay. So in quantum mechanics, we use what's called measurement incompatibility to model the violation of Bell inequalities. This is something that is in the literature since about 1980. So for Alice, quantum mechanics uses measurement operators A and what I'll call A rotated, which is so we use A if the random number is 0 here, and we use A rotated if it's 1, because then the modulation of the polarization has happened. And so we have these 4 operators, and for all of those, the measurement results are plus or minus 1 to tell us which of the 2 APDs triggered. And so because those values are both plus or minus 1, we have the square of each of those is equal to 1. Now, Alice and Bob are far apart, so quantum mechanics says that A and A rotated are compatible with B and B rotated, and so we write that as A and B are compatible with each other. This expression is equal to 0. But because we can't have different electro-optic modulator settings at the same time, either it's 0 or it's 1, then we say that A and A rotated are not compatible. This expression is non-zero, and the same for B and B rotated. Then we can write down a measurement operator C that corresponds to what we did on the previous slide, the calculation for the 0 and 0 settings for the 2 modulators. So we have A and B, the product of those, and the product of A and B rotated, A rotated and B rotated, and so on, with a minus sign here, so that when we take the square of this object, 8 of the terms of the 16 that we obtain cancel. And we're left with just these 8 terms where A and A rotated, the incompatibility between that and the incompatibility between B and B rotated, we take the product of that, and that adds onto the 4 that we get for the other 4 terms that don't cancel. Now in classical mechanics, as usual, measurement incompatibility is just not allowed. It's unclear why, because this causes classical mechanics to be what we might call computationally incomplete. Because c squared is equal to 4, that means that a value of on the previous slide that was 2.714 ought not to be more than 2. So the fact is, however, that we can introduce measurement incompatibility into classical mechanics, giving us what I call CM+, because it's more capable. It's as capable, indeed, as quantum field theory or quantum mechanics. So that's what we would want to use if we were going to, if we want to describe this experiment in this kind of way. Now, the Bell literature is huge. There's a considerable part of it concerns itself with non-locality. But if we're talking about noisy fields, and indeed about quantum fields, then there's an idea called microcausality, which just says that locality is closely associated with measurement incompatibility. So when we've said up here that there's measurement incompatibility between things which are close together, but no measurement incompatibility between things which are far apart, that's precisely what microcausality says. So for classical mechanics, that's perfectly reasonable too, it seems to me. For classical mechanics or quantum mechanics, if measurements are far apart, they don't affect each other, but if they're close together, then perhaps A and A rotated ought not to be thought of as compatible, because after all, classical physics is quite capable of saying, I can't have the electro-optic modulators be the same setting at the same time, different settings at the same time. So another aspect about a noisy field is, as I said on the first slide, a noisy field is much less like classical particle physics than it's like the heat equation, which depends on boundary conditions. If we have hot on one side and cold on the other side, then the gas, or whatever it is that's contained within the apparatus, knows about those boundary conditions all too well once it gets into a steady state. So we have temperature measurements are indeed very like measurements in quantum field theory, where what we find is that in quantum field theory, as for temperature measurements, their measurements are approximately local, but they're never actually point-like. You can only measure in quantum field theory in small regions. So Bell's theorem, as it was originally constructed by Bell in 1964, isn't appropriate for a noisy field. And so Bell wrote a new article in 1976 called The Theory of Local Beables. And for this, we talk about A and B at the time of the measurement. And then we have down here what happened in the past. And so in this diagram we have A, and we have what happened in the past corresponding to down here. And there we actually measure A and B and C, things about the apparatus, and we actually record that data. At the same time, however, we can't possibly record everything about what happened within the apparatus in this larger and larger and larger region. And so there are things which are not calculated, which are not measured, lambda and mu and nu in these three different regions of space and time. Now it turns out that to derive a Bell inequality, one thing we require is that there must be no correlation whatsoever between lambda and mu for any value of nu and for whatever the measured values of A, B, and C are. Now, for photons, what's required is fairly obvious for photons, for particles. The value of the recorded measurement result for A for any photon can't depend on Bob's choice of what to measure or on its outcome. But for a noisy field, what we have to say is that the value of A cannot be correlated with any aspect of what happens near Bob. But the whole point of the experiment is to ensure there are correlations between A and B. But we're going to insist there can be no correlations whatsoever between lambda and mu, between A and mu, between lambda and B, and there's a considerable number of other things that have to be just right. But consider, a correlation that can be measured easily now is often almost impossible to measure even moments earlier. So if we're looking at a hillside and there's a landslide about to happen, it's not possible to predict to within a second or two when the landslides are going to happen until after it's happened. Then, yes, we can record that it's happened and the time that it's happened at. An avalanche on a hillside is not different from an avalanche in an avalanche photodiode, according to this noisy field kind of approach. So if we think about an experiment in terms of noisy fields, it somewhat changes how we think about what it would be interesting to know. When Gregor recorded this data, he explicitly waited until the system is at a steady state so that the data at the beginning and the end is more or less the same. But what happened before he turned on the power? Presumably at some point in the past there were very few events, and then when he did turn on the power there started to be lots of events, and then there started to be events and coincidences, and then events, coincidences, and indeed the events are mostly green and yellow in this color scheme. So are those three delays exactly the same? The change from very few events to lots of events happens at more or less the speed of light. But do the events and coincidences happen a bit slower? Do the events and coincidences in green and yellow happen at a tenth of the speed of light, say? This is to really investigate what the cause of that steady state is, how it came to be. We can also ask not just what happens when we turn on the power for the central pump, we can ask what happens if we do more subtle changes, like change the intensity of the light on whatever schedule you like, and see what the response is to each different change. And it will be nonlinear in general, so there will be complications here. So another thing that the literature thinks about considerably when in regard to the Bell inequalities is free will. So if it bores you, turn off now. My wife and I often have tea in the afternoon, so perhaps there's a 60% chance we both have tea at the same time, which I suppose is not a coincidence. But that 60% correlation is at most a small constraint on our free will. I can say no tea today and be perfectly happy. Even if there was 99% correlation, I can say that. But if I said no tea today a lot, we might decide that the correlation has changed. We might say that we're falling out of sync. But perhaps next week will be different, and we'll have tea a lot more. And we'll get back to the long-run statistic, what we described by the 60%. So I think of probabilities as beliefs about or expected but not compulsory values for future short-run or long-run or longer-run statistics. And of course, the literature on probability and statistics is huge, so this is a very glib sort of claim, but it seems to me that statistics are descriptive and probabilities don't constrain my free will. Hardly at all, unless I think to myself, I want this long-run statistics to be at 60%, in which case, yes, I've chosen to allow myself to be constrained by that statistic. So now, in the particular context of a Bell inequality experiment, suppose we let Alice and Bob decide their settings, but Bob says, I'll always choose one. That'll be a good joke. That'll show them. The experimental protocol will tell Alice and Bob to do it again. Someone else has decided the experimental protocol would be prescriptive. It insists that Alice and Bob will choose randomly, and they won't choose randomly, say, starting at the same bit in a binary expansion of pi. Alice and Bob presumably have agreed to that. They said, yes, we will choose randomly. So when Bob says he won't choose randomly just for a joke, then he's breaking the protocol, and that is very different from him not having free will. So if we can't trust Bob, then we have to have hardware decide. And indeed, there's another aspect of this, which is that the hardware has to decide at megahertz rates. Because it's around about 2 microseconds, a bit longer than 2 microseconds for light to go from Alice to Bob, we want to change the setting to the modulator fast enough that when Alice has a measurement result, the measurement result at Bob can't know what that measurement result is. Now, there's an awful lot more we could say about quantum mechanics, about Bell inequalities, and particularly about the measurement problem, but I'll stop